In the last section, we talked about the derivative of a function at a point. Now we're going to talk about the derivative of a function as a function in its own right. But before we do that, let's review what we learned about the derivative at a point. So let's suppose we've got a function y equals a function f of x, and we often like to draw the graph y equals f of x. And we want to say, what do we mean by the derivative of f of x at this point? Well, our basic idea was that it was the instantaneous rate of change of f of x at x equals a. So as we increase x, how fast is f of x changing? And we saw that that was the same thing as the slope of a tangent line. If we draw the line that's tangent to the curve at this point and take its slope, in this case it looks like it's around -1, that's going to be the instantaneous rate of change, and it also gives us a conversion factor. If you increase x a little bit, how much are you going to change f? Well, roughly you're going to change it by the slope times the run. The rise is the slope times the run. As long as you stay close to a, you're going to stay close to the tangent line, and that's a pretty good approximation. So it was a rate of change, it was a slope, and it was a conversion factor. It's all three things. Now we want to look at a function. Now this is how I think of a function. A function is a machine that takes numbers and spits out numbers. Now in this case, it might take the number 1 and spit out f prime of 1. It might take the number 2 and spit out f prime of 2. It might take a number a and spit out f prime of a. And we call this the f prime function. So the idea is that the value of f prime at a particular point is the derivative of f of x at that point. Now, usually when you have a function, you want to have a formula for that function so you can actually go out and compute it. Well, we know that the derivative of f at a particular point a is the limit as x goes to h goes to 0 of f of a plus h minus f of a over h. So there's the formula for our f prime of x. F prime of x is the same thing, only with x playing the role of h, because this is sort of the general form. If you want to do this and then plug in x equals a, you get this. And that's the derivative at a. So let's work an example. The example is a pretty simple function. It's the function f of x equals x squared. If we wanted to figure out what was the derivative at 1, we knew how to do that. We take f of 1 plus h, that's 1 plus h squared, minus f of 1, that's 1, divide by h, and take a limit. And we do a little algebra. We expand that out. We discover that the 1's cancel. We get h squared plus 2h over h. Oh, that's h plus 2. Take a limit as h goes to 0. You get 2. Wonderful. F prime of 1 is 2. If you wanted to know what f prime of 5 was, you could do the same kind of calculation. 5 plus h squared minus 5 squared over h. You expand it out. The 25's cancel. You divide by h. You get 10 plus h. Take a limit as h goes to 0. You get 10. If I'm going too fast for you, pause the thing, look at the screen, work it out yourself, and then hit play again. We could do this at an arbitrary point. It's really the same calculation we did at 1 or at 5. A plus h squared minus a squared. Well, let's see. A plus h squared is a squared plus h squared plus 2ah. And you subtract off the a squared. So you have h squared over h, that's h. 2ah over h, that's 2a. The limit of 2a plus h is 2a. And instead of calling it a, we could have called it x. So f prime of x, the derivative of x squared, is given by this calculation. We take f of x plus h, that's x plus h squared, minus f of x, divided by h. Expand it out. The x squareds cancel. 2xh plus h squared divided by h is 2x plus h. We take the limit of that as h goes to 0, and we get 2x. And now we can draw a picture of what we've just done. We started with a function y equals x squared, and we derived a new function out of that, and the new function was f prime of x equals 2x. Maybe we should give this a name and call this g of x. So the function g of x was derived from f of x, and that's why we call it the derivative function. And if you look at any point in the curve, like over here, you'd say, what's the derivative of y equals x squared? Oh yeah, it looks like the slope is about, say this is point 1, the slope is about 2. Sure enough, the value of the 2x function is the slope of the x squared function. Over here, the slope is 0. Over here, the value is 0. Over here, the slope is negative. It's going downhill. Over here, the value is negative. The whole idea of the derivative function is the value of the derivative function at a point gives you the derivative of the original function at that point. Okay, we'll work out a bunch more examples in the next video.